Howdy. Today in class we talked about the idea of differentials that allow us to compute approximate changes, dy, in a quantity by using the tangent line to create a local linear approximation. And so we define the quantity dy as f prime of x times dx, where y is equal to f of x. And if you're puzzled by this, keep in mind that f prime of x is spelled in Leibniz notation as dy dx. And so what we're doing is multiplying the rate of change dy dx times dx, and in the Leibniz notation it appears algebraically as if we're simply canceling the dx's and getting the change dy. That isn't really what's happening here, but that concept is so good that it is a useful way to think about it. So we have rate times change in x equals change in y. And what we did in class was to talk about how the area of a circle might change if the radius changed. But I want to consider a second use for this idea of differentials, and that is to compute the error in a computation as a result of an error in measurement. We call this a propagated error. So we have here a circle has a radius that is measured to be 4.0 plus or minus 0.1 centimeters. What is the uncertainty or the propagated error in the area? So let's depict this situation. What I have is a circle, and I measure the radius of that circle to be 4 centimeters. But whenever you measure a quantity, you're going to have a little bit of uncertainty. And so it may be the case that the radius is actually 3.9 centimeters, or it may be the case that the radius is actually 4.1 centimeters, and as a result of this uncertainty, in the radius, there's going to be just a little bit of uncertainty in the area. I see that I'm having trouble getting all my circles to be concentric. That's pretty good right there. So my radius could be anywhere from 3.9 to 4.1 centimeters, and that's the meaning of this 4.0 plus or minus 0.1. And so we want to know how much uncertainty is there in the area. Well, we could compute this exactly simply by taking 3.9, area of 3.9, and the area at 4.1, and subtracting from that the area at 4.0. And that would tell us how much uncertainty there is exactly. However, we can approximate this much more easily by using the idea of a differential, because if you look at this, what this is really computing is a change in the area. Both of these are computing changes in area. And so I can estimate the change in the area with the differential change in the area. And all I need to know is the formula for the area of the circle. So since the area is equal to pi r squared, then the differential change in area is equal to the derivative, let me write it out explicitly, a prime of r times the change in the radius dr, which is going to be equal to 2 pi r times dr. And now the dr is going to be, in previous problems, the dr was the change in the radius. Here, we're going to think of dr as the uncertainty in the radius. In other words, if the radius is 4.0 and it's uncertain by plus or minus 0.1, then my radius could change on me by plus or minus 0.1. So that if I now plug in, then what I get is plus or minus 0.8 pi centimeters squared is the differential change in the area, which we're going to call the propagated error, or the uncertainty in the area. Now, sometimes we are interested in knowing how big is this error anyway? Is this a lot of error or a little error? Well, if I multiply it out, you can see 0.8 times pi is going to be about 0.8 times 3 is about 2.4 square centimeters. Is that a lot or a little? It kind of depends upon how big the figure was to begin with. And so very often we're going to be interested in the relative or percent error. And the relative error compares the error that we got, the propagated error, to the size of the original. And if I want it as a percentage, the percent error would be the same idea, times 100%. And so when I compute the relative error for our circle here, we got 0.8 pi centimeters squared, and the area that we compute is the area at the baseline at 4 centimeters. So that would be 16 pi square centimeters. And when the dust settles, then we get 0.8 over 16, or 8 over 60, which is 0.05. And that gives us a percentage error then of 5%. In other words, we have an uncertainty of about 5% in our original computation.